Can a 5-digit number, now y'all, we normally mean integer here, in common letter used for integer, comprised distinct even digits be a perfect square? Now, I notice I didn't say comprised of. I was told by a grammarian that that's lately considered incorrect. I say comprised distinct. I didn't leave out of. That's how I used to say it. Da, da, da. All those English conventions, da, da, da. They change over time for very pretentious people. Now, y'all, right here, we want to know if this can be a perfect square. Now, an example of something that is in this form, 5-digit number comprised only of even digits, would be 8264, right? That meets the requirements because there's only 5 even digits, right? So this is kind of the threshold. It's a 5-digit number comprised distinct even digits. I have to fight hard not to say of. Be a perfect square. Well, this is a number that's in that form, and it ends in 64, which is a perfect square, but it's easy to verify that this is not equal to k squared. Okay, so that's just an example. We want to prove it in general. Okay, I want to prove it in general. Let's move along. Now, another result that's super important, and it's based on the fact that 10 raised to the n, where n is a non-negative integer, I think. Yeah, you don't want negatives here because I give you fractional stuff. We're not interested in that in number theory. But this is always congruent to 1 mod 3. Now, y'all, what that means is if you, like for example, a simple example, if your n is 2, you would get 100 minus 1 is 99, which is a multiple of 3. The same is true for mod 9, which is slightly more popular. But this is actually easier for this problem, okay? Now, so since 10 to the n is congruent to 1 mod 3, all those powers of 10 become 1 right here, you see? That's really, if you think about what this number would look like, it would be various powers of 10, but they're all just 1. So they all just go away, and these are the only even digits, 0, 2, not necessarily in this order, but you would add up these digits right here, and you would note that this is equal to 20. Isn't it? 14, 18, 20, it's equal to 20, but that is congruent to 2. And of course it's mod 3. 20 is congruent to 2 mod 3. Now, there's a result here, and I'll prove it for you, but it's any integer squared is congruent to 0, 1. Now, if we just assume this is true, then we realize that we're done right now, okay? Because any 5-digit number with 5 distinct even digits is going to be congruent to 2, all right? And it can't be according to this limit. So QED proof is complete, right? That means we've proved it. So we are done with the proof if you accept this as the truth. Now, if you don't see why this is true, all you have to do is consider 0 squared, which is certainly congruent to 0 in any modulus, right? 1 squared, God, I put an I there. Okay, 1 squared is congruent to 1. And remember, any integer at all leaves a remainder of 0, 1, or 2 when divided by 3. So you only have to check those values. Now, 2 squared is equal to 4. That's the only one that's interesting here. And that's congruent to 1, right? So you see, this proves this lemma. And again, the basic idea here that bothers some people is that any integer you can think of is congruent to 0, 1, or 2, right? Well, we've just checked the squares of all of those, and we just get 0 or 1, right? So that's why this is true, folks. This came out of T2 and Driscoll's 104 number theory problems. It wasn't considered a difficult problem, but you did have to think of a couple of things here. You could do it mod 9, but there's no real reason to. Mod 3, I guess, is slightly less work, if you want to say so. But anyway, that does it, folks. It cannot happen. Thank you for viewing.